Hello, my name is Marek, and I'm going to present you our current research about backward symbolic execution. Let me give a brief outline of the talk. First, I'm going to talk about regular symbolic execution. Then I get to backward symbolic execution and its connection to K-induction. And at the end, I will show you how we infer loop invariants using loop folding during backward symbolic execution. And I will also show you some results that we achieved with our technique. Let me start with some preliminaries. We are going to represent programs as control flow automata. A path in a control flow automaton is a sequence of successive edges. We are concerned with the problem of the reachability of the error location, which is shown red in this picture. That is, we want to find out whether there exists a feasible path from init to the error location in a given control flow automaton. One way how we may find it out is to use symbolic execution. Symbolic execution is a technique that incrementally enumerates all possible paths in a program. It starts in the initial location of the control flow automaton and replaces the values of all variables with symbols that represent arbitrary values. Then it starts executing the automaton. Here, for example, the first edge is executed and a new state where x and I are assigned 0 is generated. We got to location 1 that has two successors. Let's try to take the edge from 1 to 4. There is a condition, and we substitute the current values of variables into the condition and check whether the expression that we obtain is satisfiable. I is 0 in the current state, and n is the symbol for n, so the expression that we get is 0 is greater or equal to the symbol for n. Since we know nothing about the symbol for n, it may be less or equal to 0, and we generate a new state that got us to location 4, and remembers the condition that 0 is greater or equal to the symbol for n. Location 4 has no successors, so the execution ends there. Similarly, we evaluate the edge from 1 to 2, generating a new state where we remember that 0 must be less than the symbol for n. Each path in the symbolic execution tree corresponds to a feasible execution path of the program that starts in init. If we continue generating the states, we get to executing the edge from 3 to the error location. At this point, we are asked to evaluate the condition x is not equal I, which is not satisfiable in the current state, and therefore this edge cannot be taken, and this path is infeasible, which is highlighted by drawing that state dotted. This way, we continue generating symbolic execution states until we can. Backward symbolic execution works similarly, but it runs backwards from the error location toward the initial locations of the automaton. In the first step, the edge from 3 to the error location is evaluated backwards, so we get that in whatever state we got to location 3, x must not equal I in that state. The increment of x and I does nothing to this condition, so we continue the execution to obtain that value of I must be less than value of n when we are at location 1. Any other step will result in an unsatisfiable condition, and as a result, we know that the program is correct. Both symbolic execution and backward symbolic execution compute the weakest precondition on the variables that make the program or automaton to execute a given path. Only each of these techniques considers a different set of paths. Seemingly unrelated is the technique called K-Induction. It was introduced for hardware model checking, but later it has been adopted also for software verification. Its principle is simple. If we have a state space represented as a transition system, we do these steps for a given parameter k. First, we check the base case, where we check that there is no error state in k or less steps from the initial state. If the base case succeeds, we check the induction step, where we check that after we do k arbitrary safe steps, we may do one more step without hitting an error state. If the base case fails, we found an error. If the induction step succeeds, it means that the system is correct. We can transfer this scheme also to paths of control for automata. Here, in the base case, we check all the paths of length maximally k, in our example k being 3. Since none of the paths in this automaton of length maximally k ends in the error location, these paths are trivially safe and the base case succeeds. In the induction step, we take all the paths of length 3 that are safe and we try to prolong them by one step. The paths that do not end in the error location are trivially safe. And if you remember the slide about backward symbolic execution, we know that the other two paths that left are infeasible. And therefore, the induction step succeeds. If you investigate the path that we search once more, you find out that in the base case, we search exactly the paths that are searched by the symbolic execution if you bounded the length of path to be maximally 3. And in the induction step, if we constrain ourselves only to the paths that end in the error location, then these paths are exactly those paths searched by the backward symbolic execution if you bound the length of path to be 4. If we perform backward symbolic execution and bound on the length of path to be maximally k, and we find no error, we know that there are no feasible paths from init to error location of length maximally k, which also means that there are no feasible paths from init to error location of length maximally k minus 1. Therefore, we proved the base case of K-induction for k minus 1. And as a result, running backward symbolic execution with bound on the length of paths to be maximally k is the same as performing K-induction for k minus 1. Knowing that backward symbolic execution does K-induction means that we know its pros and cons. In particular, we know that backward symbolic execution is incomplete. For example, if we move the assertion in the program from our example after the loop, backward symbolic execution does not terminate. This problem is usually solved, at least in software K-induction, by using invariants. These invariants are usually injected directly into the code. We extended backward symbolic execution with a technique called loop folding that also infers invariants, but it infers the invariants directly from backward symbolic execution states during the execution. To briefly sketch how loop folding works, assume that we have a loop with the header h that has two paths pi1 and pi2, and backward symbolic execution finds a feasible path from h to the error location. The backward symbolic execution states give us this red set of states phi that make the program reach the error. To prove that the program cannot be in state phi, we create a first invariant candidate xi0, which is a set of states disjunctive with phi and which is inductive on h. That is, whenever we execute the program from h and we are in these states, then if we get again to h, we are still in the states xi0. If xi0 is not an invariant, we compute its preimage over each path of the loop. Then we over-approximate these states that we got to psi1 prime and psi2 prime, such that these new states are still disjunctive with the error states. These over-approximated states, together with xi0, are new invariant candidates. If neither of them is an invariant, we continue the process by computing the preimage of the lastly created invariant candidates. And this way we create new candidates and we continue creating new candidates until we either find an invariant or we hit some bound. If we hit a bound, we give up loop folding, but we store all the candidates for further use. And if we ever hit the loop again, we take the candidates that are disjunctive with the current error states, We merge them together and use them to create a new first inductive candidate in this new loop folding attempt. More details about loop folding and how it does the over approximation can be found in the paper. At the end of the presentation, I would like to share some experimental results. We ran a set of experiments on benchmarks from the Competition on Software Verification 2021 on the category loops. This category has 770 benchmarks. We compared BSELF to backward symbolic execution and also to the tools that performed well in this category in the competition. The results that compare BSELF to backward symbolic execution are as one would expect. On many benchmarks, backward symbolic execution is faster than BSELF, which is demonstrated by these black crosses in the scatter plot. 4 benchmarks were solved only by backward symbolic execution. Those are the red crosses. And there are many green crosses, which are benchmarks solved only by BSELF. The fact that BSELF clearly beats backward symbolic execution can be seen also from the quantile plot on the right that shows how many benchmarks would backward symbolic execution or BSELF solve if the timeout on one benchmark is set to the value on the y-axis. This table shows the number of all decided benchmarks by the tools that we experimented with, and also the number of decided benchmarks that were non-trivial. Non-trivial were benchmarks that could not be solved by symbolic execution or bounded model checking, that is, by the simple enumeration of state or path space. There's not much time to comment on the whole table, but if we compare BSELF to on the non-trivial benchmarks, it can solve more benchmarks than other tools that use K-Induction, that are the tools in the top part of the table. We also ran a configuration that uses symbolic execution half of the time and BSELF half of the time, so that the non-trivial benchmarks are solved by the symbolic execution, and then the rest is left on BSELF. And this configuration was beaten only by VariApps, which is a very optimized tool. And this is all that I wanted to show you about our technique BSELF. And for any other details, please check out our paper. Thank you for your attention.